Okay, so now I'm going to take the next step in our lab, which is to figure out the Mannings coefficient. So Mannings coefficient is a roughness indicator. Not every surface of a channel is smooth. There are a lot of rocks and vegetation and many things that can cause it not to behave like a perfectly smooth flume. So Mannings is kind of an empirical um, coefficient that you can apply to streams to account for that roughness. We have velocity that we measured, and we have the slope. We have the hydraulic radius. So what we can do is back calculate our Manning's roughness coefficient and then compare that to what we get in the handout from Canvas, which is this Van Haveren. So I just did a couple quick calculations so that we can get the hydraulic radius for the velocity cross-section, which again is different than the topography cross-section that we had before. So I got the straight line distances between all these points. They're going to be really close to that 1.4 spacing of each of our rectangles. So straight line distance to get the wetted perimeter plus the top width. That'll be the total wet perimeter. So let's just add those together and get the the hydraulic radius. So we'll add this top width to our sum of all the straight line distances. Notice how I included those water surfaces, right and left edge water, when doing the wet perimeter. And that's because we added those points in because they're actually where the water ends. So this is what I mean by field conditions, where the water is at the time of the survey. So our hydraulic radius is the area divided by the wet perimeter. Okay, so that's the R that we're going to use in this Manning's calculation. For S slope, usually you're talking about the energy grade line slope, but it's very, very common to just use the slope of the channel, which is what I'm going to do here. We'll just do it simple way, rise over run. So I'm going to use the first and last points. So we're going to do this minus. So that's our rise over our run. Okay, 0.0015, which actually happens to be the average if you were to take the slope of the middle and the first and the middle of the last point. So our slope is 0.0015. My Excel sheet's a little bit messy here. Okay, so now we have what we need to plug into Manning's except for the velocity. So this velocity here, this is where I'm going to use that average velocity that I got from our total discharge. So Q equals VA. So if you've got the total Q and the total A, your average velocity is going to be Q divided by A. This is basically a way of kind of normalizing all the different velocity values that we get and get a representative velocity for the entire channel. Okay, so we're going to do equals our Q that we got divided by our cross-sectional area. Okay, so that's our average velocity. Just to compare that to what we had here, let's average this and see if it gets close. Not really. See, this is actually a lot more. So let's back calculate n and see what we come up with. So first we have to solve for n. Just doing a little algebra, you would basically just switch the places of v and n equals v times r to the 2/3 and s to the 1/2. So I'm just gonna do that. N equals r1 over b times, I always use way too many parentheses because I'm scared of parentheses. But it's better to be safe than sorry. Okay, so our n here is 0.049. Does that make sense? Now I'm going to go to Van Haveren, which I have pulled up here, and let's see if I can find the best description of our stream. So we don't have an excavated stream. It's a natural stream. This is a mountain stream. We're in the Poudre Canyon. And so do we have cobbles, boulders, gravels? There's some gravel, but it was actually mostly cobbles. So our 0.49 actually makes perfect sense here. Somewhere in between the low and mid-range of this number 2 category. So 0.05 would be a good guess. Again, if you disagree, you are welcome to choose something else. Okay, so we just got that our back calculated Mannings coefficient is 0.049 and then verified it by looking at the Van Haveren document. I have now switched over to the original spreadsheet where we were looking at the entire cross-section that we got bankful from. And so here are our calculations from bankful from the previous videos. What I'm going to do is use Manning's equation and the Q equals VA formula to try to calculate my bankful discharge with that Manning's coefficient that we got. It was 0.049, so I'll just use that.